All right, welcome everybody. This is Fred Schenkelberg, and today's Accendo Reliability webinar is about one of my favorite topics. And I realize, and which is why I'm talking about it, is not my favorite topic for a wide majority of people. And there are many, many reasons for that, and there's many issues with that. But in reliability engineering, like in many parts of engineering, we have to deal with things that vary. And statistics, probability and statistics, is a vehicle or a language or an approach that we can use to deal with that variability, that variation piece. And so that's the short answer of why we use statistics. But let's explore a couple different things and some of the ideas behind, I think, probably a better title would how we should use statistics would be a way to look at this. But either way you approach it, hopefully we'll have a few good discussions along the way. And so one of the first things that's interesting about statistics is that, and math in general, it allows us to explore the phenomena that we see around us and around the world and about us. We can examine patterns, we can spot properties, we can do all kinds of different things that allow us to form a question, gather some data, and then answer that question sometimes. But the basic idea of most of what we do in math and in statistics is exploring, is what's going on. How does this table of numbers or this compilation of observations translate into something that we can use to learn more about what's happening in the systems and processes and patterns that are in the world around us. Now, part of that exploration part is then understanding what's going on and getting some ideas of a way to describe, say, a cumulative distribution function. What's the pattern of failures for this particular type of failure mechanism? And with that understanding comes another round of insights and ability to explore and compare and so on. But the ultimate idea is the models that we create allow us to peel back that onion a little bit to understand how it works. And so creates some level of understanding. Now, there's a double-edged sword here. There's a part of statistics that if the model isn't really representative of what you're trying to understand, you can be misled. And everybody has probably heard of the famous book from years and years ago that was the How to Lie with Statistics. And there's plenty of ways that people can use statistics. Maybe I should say that there's 87% probability that many people, say 48% of the population, suspect that most statisticians or statistics that they see is meant to mislead them. Now, I have no idea what the real numbers are. I just made those up, but it gives it a bit of credibility when you put 2 or 3 significant digits on a number, independent of whether it's true or not. And that's a problem. So with understanding comes the ability for us to explain what's going on, how we got to that, what were the underlying assumptions, how this model is supported by the evidence that it represents the phenomena that we're trying to understand. Done well, it helps others understand. And that's a key feature of why we use statistics, is that done well and representing what is happening and being able to explain it in a clear, concise way allows other people to understand. And that's a beautiful part of the language of statistics. And although so many people, and myself included, have used statistics more like a club and to not deliberately mislead people, but and some have, I suppose, but to say, trust me, here's the math. And that's not always a good, I don't think it's ever a good approach. But I've learned that the hard way. It's being able to understand what's going on and help others understand it is a big part of why we use statistics. Even though many people, roll their eyes as soon as you open up a stats book. But we got to get over that. Another big use of statistics is comparisons, where vendor A versus vendor B, process A or process change versus the process normal, this design versus that design, also comparing what we're trying to do versus a standard. And so we do lots and lots of different kinds of comparisons, and it allows us to detect differences that may not be obvious just by observation alone. And so using charts and graphs and techniques and methodologies like hypothesis testing and others allows us to really understand the differences when they are real and versus when they are just random. And that allows us to make conclusions, to understand a bit more about what's going on and what differences are real differences. Because underneath all of this stuff, everything we deal with varies. And so it's a good part of what we do in statistics is a bit of exploration, a bit of understanding what's going on and modeling, and a lot of comparisons. And so that's a broad overview of why we use statistics, but let's jump into how do you use it? What kinds of tools or techniques do you use? And I'm going to mention a few in this presentation, but I know we got a good audience today. So what kind of math do you do, or statistics do you use or do? Hopefully nobody's going to say MTBF. There's actually been quite a bit of chatter on LinkedIn. I get copied every now and then now by people that are kind of taking up the call to get rid of the use of MTBF for all kinds of reasons. So I take that as a sign that more and more people are starting to understand statistics a bit more and trying to understand what's going on. Exploratory data analysis, that's an excellent one. Byman, I've drawn a complete blank on the guy's book. But there's so many things you can do with, well, what are actually very simple graphics and ways of peering into stuff, and then very sophisticated computer aided ones where you can get 3D clouds and you can rotate them and see 3 different variables, how they interact, and then you could play in with different dimensions. And there's some amazing things you can do just by getting the data visible. It's one of the very first things I learned in statistics is plot it. If you got a stack of numbers, plot it. Find one or more plots and just put it on paper and or the screen and see what it looks like. T-test, hypothesis, yep. The comparison's good. Regression analysis, great. Ninja, yeah. All good, and all good tools. And hopefully in and among each of those, and for the rest of you, is many other types of tools that we use on a regular basis. And of course, there's depths of each one of these kinds of things, but even a simple plot is a start of using statistics. And so we're going to explore a few of those. And so there's lots of ways we depict variation. And statistics, I've been told and read a number of times, it's the language of variability or variation. And so we know that no 2 products we put out will be exactly the same. There's going to be material differences and subtle differences in the way it's used and how it's used and what the expectations are around it. There's things that we can control and minimize the variability of, and then there's other things that we really can't. And yet at the way things work and the way things pick up defects and wear out and so on, all varies. And so here's a quick exercise. Hit the chat window and just pick a number between 0 and 10. So 1 through 9, the basic integers, just pick a number and I'll plot them here. If I can get my cursor to behave. Do that. All right. So I got a 7, a 9, 3, 3, 3, 9, 5, 7, 4, 5. All right. Did I get them all? I think I was keeping up there. Any more? Yeah, Zubin is the last one I had. Right. So is that a random process? Would be a basic question that a histogram could tell us. If you are looking at a set of data and you just wanted to know, let's say if I'm rolling a die, a 10-sided die or a 9-sided die, or I guess I only have 9 numbers here, 9 integers, I would expect, something that would be uniform, right? That there would be a 1 in 9 chance of each one being picked equally. Well, we got 2 counts on well, there's an odd number, but bias, there could be. Yeah, it looks like that. We only have 4 as our sole even number representative. But if we kept this going, and there's a handful of papers out where people have studied it, and I've had, larger sets of data of people doing this, and it's a phenomena that people are absolutely horrible random number generators. We pick 3 and 7. And those will dominate. And then some people say, well, I think of 7, but I want it to be random, so I'll pick 6 or 8, or I'll pick, I want to say 3, but I'll pick 2 or 4, if you think about it a little bit. And then others that have a little bit of a statistics background, they might have actually, well, let's pick 1 or any of them, or look at a clock, or do some other technique to truly create a random pick. The humans, if you're running a process and want to do a random sample, which is important for many of our sampling processes, just picking a number is probably as least random as you can get, right? But a histogram, just doing a simple check mark tally of these things, a simple count, and with more data in a spreadsheet or something, you can do frequency plots. You can automate these, you can make them bar charts and all kinds of fancy ways to do it. But even just a quick, simple plot the data set on a histogram provides an insight as to what's going on. And if you don't automatically start going, well, that should be this, and it looks like this. Why is that different? In histogram is the foundation of depicting variability. Now, if everybody would have picked 5, which was feasible, it would be technically possible, right? There's a finite chance that everyone in this audience would have picked a single number. We usually don't. And if you look at data sets and you say you're monitoring a process or making measurements on prototypes and so on, just a histogram and a dot plot or a handful of other of these very basic tools that you can do by hand easily provide a bunch of insights as to what's going on. Because we already see that there is some variability, right? And let's see, we got 1, 2, 3, 4, 5, 6 values here and 4 over here. So looks like 5 is kind of our average, give or take a little bit without doing the calculation. And we've got a spread. It's not quite uniform, but it almost is, right? We almost have a uniform distribution. So, that's not too bad. If we would have continued this on, I know from previous experience and studies that have been done is that we would have a 3 and 7 it'd be a bimodal type distribution. So it's again, if you're needing to pick a random number, pick up some dice or open a book, or Excel's random number generator is not all that good. So if you got $1 million project, put a little effort into it. But I digress. That's a whole separate discussion. So let me clear that. Get rid of my drawing thingy. All right, thanks for participating in that. All right, CDF. We use these a lot, and it's kind of a regression analysis, right? We're fitting a line, say a Weibull distribution, to a set of time to failures. It's not as simple as an XY plot, right? It's a little bit more sophisticated. We use the maximum likelihood estimators lots of times, which is a more advanced technique, and happy to have computers doing that with us. But what we get is a representation of what's the probability of something lasting for some amount of time. So roughly, whoops, let me get my drawing thingy back up. If I can get my cursor going. Let's see, annotate, draw. So if we're interested in when half of our units fail, we come down here and say it's maybe 60 months. Now that may or may not be suitable for what we're trying to do. And we can make a decision based on that. Or if we ask a question is, well, how many will last for 48 months? And we find 48, go over here, and is 30% okay or not? You know, what's an appropriate value there? And then we can balance that off our financials, our warranty expenses, customer expectation, all of those other things that matter, right? We don't create CDF plots or Weibull plots just because they're cool, which they are, of course, but we create them so that we can ask and answer questions. And later you can use these to make comparisons. You can do all kinds of different things with them. But creating one of these is either field data, if you got decent information about the failure mechanisms, doing accelerated testing, vendor data, all kinds of different ways to collect the data. But it provides a much better insight to what's going on than a table of numbers. And it allows us to, we could use the same data set and fit this regression values for, say, the beta and eta values, and we could do PDFs, much like a histogram, or we could do hazard functions, and we could do reliability plots. And each one has its own purposes for asking and answering questions, but it's the sequence of questions that's most important, whether it's a histogram or a CDF. Yeah, creating them does take some skill to get it clear. Even a histogram, if you got a good set of data, say a couple hundred points, if you change the width of the bins that you're putting numbers into, you'll get a different looking result. Not all the time, but some data sets are very sensitive to what the bin widths are. And so that takes a little bit of what's really going on here, what tells the right story. CDFs, I mean, you can add confidence bounds and do all kinds of other fancy stuff with these things. Yet, just the basic CDF, when I get a set of data that is representing time to failure or cycles to failure, things like that, I'll put it on a Weibull plot. Weibull might not be the right regression or the right distribution to describe it, but usually you can get some insights just by doing that, or even a simple histogram, a PDF. Let's get some ideas of what's going on in that data set, and then move on from there to refine the regression, find the right distribution, which depiction of that data set is going to give you the ability to ask and answer better questions. So that's a common tool that we use, and it's a simple, relatively simple plot. I used to do these by hand. I don't remember the last time I have, because we have such great tools these days. So these are pretty simple to generate. They take a little bit more effort to explain, yet I've often found that even mid-level managers can understand these plots pretty quickly. And it helps them dive deeper into what the data means. And so that's a good thing. All right, get rid of that. I have to bounce between the annotation tool and the ability to move forward. There we go. Variance. The language of variation is variance. It's we have a mean, and we use mean, median, and mode. Mean very often to describe where's the center of balance. So where's the center of mass, I should say. And that's considered the first moment in statisticians' terms. Variance, not standard deviation, but variance is the second moment. And it's the statistician's use for how the spread of your data is. How variable is it? How far away from the mean will your data likely exist? And how's it set up? Now, neither mean and variance alone tell you what's the shape look like. Is it a nice bimodal, normal distribution thing, or is it skewed one way or the other? Mean and variance don't tell you that. You have to go to the third moment and fourth moments, the skewness and kurtosis, to get a better insight into that, if just using these measures of data sets. Now, one of the things I ran into, and I happened to have this image on this slide, and as I was putting the notes together, says, I don't know if it would be fair to ask everybody what's the mean of a 20-sided die, and then what's its variance. Now, the variance, when I did the calculation, I looked it up actually, is 33.25. Now, I found that surprising. There's only 20 options here for this die to give a result, 1 through 20. But the variance is larger than that. And I said, oh, wait a second. The variance is the square of the standard deviation. Standard deviation is in units that are similar to what we count in. So the standard deviation would be between 1 and 20. It would be in that realm someplace, usually, not always, but on a fair die that's in a uniform distribution, it would be, less than what the mean is. The variation would be some smaller number to it. And what trips up so many people is that the variance is the square of that standard deviation. And so it's not intuitive to me how to interpret a variance of 33 when I have a 20-sided die. I don't know how to translate that. So I almost immediately take the square root of it and get the standard deviation so that I can take a look at it. Now, if it's truly a normal distribution, if I roll this thing over and over again, or say I had 5 or 6 of these and I'm averaging the results, then I would get a mean and a standard deviation that would be representative of a normal distribution. But if I'm only using one die, I should get a uniform distribution. But the mean and standard deviation are identical, right? Now, if I have more die, I'm probably going to have if I'm not taking the averages of those, but just taking the cumulative number, what's going to happen to the variance and to the standard deviation? Right? It goes up. The more things that are interacting with our system, the more random elements that could be higher or lower than its typical average or typical value means that the variance gets larger. The standard deviation gets larger. So if we can control a process and have one lever, say just the temperature of this one critical step, and we control that, we can significantly control the variance, the variability of that process. But if our process is like the height of human beings, it's controlled by genetics and by diet and by exercise and on and on and on and on. If you had illnesses or not, whether you broke your arm or not, whether you have good posture or not, a gazillion different variables. And some add to your ability to grow to a height, and others detract from your ability to achieve that height. And so we have all these small perturbations, and you know where I'm going with this, is then we end up with a normal distribution of human height, because there's so many die at play. And so one of the things about variance and why we use statistical tools to talk about it and depict it and graph it and so on is that it's a complex world we live in, and the products we make and the systems we manage are complex. And lots of dye are being used to create bits and pieces of variability. And so our ability to explore that, to examine it, to understand it, allows us to find those critical few that allows us to monitor and sometimes control or minimize the amount of variability that's coming out of that process. All right. And whether it's in our designs or in the manufacturing or in the process world, it's the same process, same basic technique. Is we're not, yeah, sometimes we want to know where the mean is, where the average value is. We want to be in spec. But oftentimes the variance, that second moment, is much more important to understand if we're going to make progress in improving our systems and processes. And so we do use the calculations of these, but they're not nearly as insightful or revealing, although we use them in all kinds of calculations and depictions, but the graphics of them, of the spread of our data, histograms in particular, allow us to see the data. And I find that to be so informative. And then add the numbers and do the calculations, but plot the data first. It's so much richer in its ability to communicate to us when done well, when done well. All right. So one of the reasons we use statistics is that it provides us insights. We get to see the data set. We get to understand what's going on with our data. And so let's say I've got a histogram. I collected some data and I get a histogram that looks like this. What questions come to mind? What's an obvious question that, or even not obvious question? What would, if you collected a handful of data and you got this histogram, what would you think? Yeah, outlier. Is it? I mean, it's the question is, I would say I wouldn't call it an outlier right away. I would say it's different, right? It lies separately from everybody else. But how do we identify an outlier, which is a vague question in statistics? If I had gathered this data, I was making measurements and writing it down. Did I swap some variables? Did I miss a decimal point? Did I, can't read my handwriting? If I still have the samples, I can go reread number 9 here and see if that was a real reading or an error. Or did something get mixed in? I was measuring screws and the number 9 reading was a nail that was in the group. What about it is different? Right? That's an obvious set of questions that a simple histogram can ask, and we may call it an outlier, but the outlier usually comes with lots of other questions. And do we throw it out or not? Right? If we're trying to say this is all in spec and our spec is an average of 5 and plus or minus 1 through 9, well, yeah, it's different. But overall, we're still okay and everything's in spec. Yeah. And JD, excellent. Yeah, there could be a couple different issues going on here. It's worth pursuing a handful of questions of what's going on. If this is my process and my spec is between 1 and 9, I'd be worried about the 2 through 4 group over here. Why is my center of mass so close to the lower bound? How do I move that more to the average, right? How do I center this process? So in context of where you gather the data, how you gather the data, how well you understand the source of the readings that you're getting, the samples that you're measuring, then helps you form into insightful questions about this thing. But just a simple histogram, and I say that it's the way to do it. Just plot it. And if I would have done just the mean and standard deviation of this thing, we could do some calculations. We could do some insights to that. We could create a mean with a confidence bound around it. We could do a couple other things. Yet I don't think that's near as insightful as just a plot. And so that's the point, is that it allows us to identify a sequence of questions that allow us to put in that context to improve our understanding of what's going on. Right. So that, I mean, that's the beauty of just a simple plot. A mean cumulative function, I'm sure many of you are familiar with this. It's basically a cumulative count over time, or over some pattern, some time is common, of, say, a repairable system. So let's say I've got this manufacturing line, and I got my, say, a bottling equipment or modeling machine. It has whirling gears and pistons and kinds of weird stuff going on in it that only a mechanical engineer would love. And over the past 4 years, we had, one failure, and then a few months later, we accumulated 2 failures and so on. But what's going on here? We have, it looks like, an increasing set of steps for each period that we plotted. What does that mean? That the rate of arrival of new failures is increasing. Now, the first time I plotted one of these things was for a escalator, and I had the same model, same basic height, same basic environment for 2 escalators, and one of them had this kind of pattern. Over the last 4 years, there was an increasing rate of callouts to go repair or fix or restore a particular escalator. The one on the other side of this platform that was very, very similar, same environment essentially, had an opposite arc to it. It had pretty high number of failures to start, and then it tapered slowly down. So it kind of flattened out the curve. And so its rate of arrivals of failures was reducing. And so one of them was being maintained by one team, another one being maintained by the other team. And it came to us basic, let's go see how they do this maintenance. What are the techniques they're using? And allowed us to say, here's some best practices. Let's use that on this machine that's plotted here. And it did reduce the recurring events. It wasn't wearing out as well. And it came down to lubrication practices. This other team, this other technician had just a subtly different way of doing the lubrication, which was much more effective at reducing the amount of wear and drag and all the other issues that come with causing an escalator to shut down. But we found, I don't know how many different escalators there were, but we plotted these kinds of things for each one of them, and each one told a story. And we could combine them for ones that were reasonable to combine, same model and make and so on, and same environments, the underground ones and surface ones and so on. And we did lots and lots and lots of plots. But every single one of these plots and this repairable data, this recurrent data, allowed us to ask questions and make observations and get insights to what was going on. Very, very useful set of plots. But it was for data set for a system that was repairable. And a couple other assumptions come into play here. Sometimes we had what looked like a piece of equipment that the curve was flattening out, and it turns out that it was shut down for 6 months waiting for parts. So it wasn't being investigated to see if it failed or not. Once it got started again, they had all kinds of startup issues, huge count and number of new failures. But these plots assume that the repairs are insignificant in duration versus the period that you're plotting. That's not always true when it takes you months and months and months to get the parts or execute a repair. And so you got to be careful with some of the underlying assumptions in many of these types of plots. All right, this one I'm sure many of you have seen before. You have a CDF, say a Weibull plot, and you're looking at your field data over time, and everything's looking good. It's got a relatively shallow slope. Things are work themselves out. It looks like we're going to make our goal for whatever 100 months translates to, and have a reasonably low failure rate. If that original part of this curve kept going, it's still on the order of half of them have failed, roughly, but wait a second, what's happening here at month 60, right? What's going on there? What would be a step that you would take to sort out what's going on? Now, for those of you in failure analysis and understand failure mechanisms, it's probably time to take a few samples and understand what causes failures for the early part versus the second part, the stick versus the blade. And 9 times out of 10, it's a change in failure mechanism, right? Something is now wearing out at an increasing rate, but early on it was insignificant amount of probability of it showing up. But at some point it takes dominance, it takes over, and it reveals itself in a plot like this. You usually don't want to see one of these with your data set, because at this point, if you see it after 60 months out in the field, that means you probably have a whole bunch of parts or systems shipped already. Now, what do you do? Right? So, yeah, and Michael, you could do 2 separate ones. With the hard part is in around where that inflection point is do you have enough data to separate which ones are failing for failure mechanism A and failure mechanism B? If you don't, you still have some evidence here that something's going on, and you can go, what? And I've seen this one where it was a product that had a compressor in it, and the compressors were failing. And so they were able to spot this early enough with only a handful of compressors had failed, but it was an obvious wear out with a beta of like 3 and 3.5. And it was going to take out all of their systems in short order. And so this thought was, well, how can we execute a repair or a maintenance step that allows the existing fleet of units that are out there to avoid that failure mechanism? And in some cases, that's a recall. Some cases, that's a patch or a fix or something you can do remotely, or sometimes it's a maintenance step that the operators can do. And it varies depending on what the details are. But by simply tracking our field data and watching for these inflections and paying attention to the underlying failure mechanisms, the more informative these kinds of plots can be. So it gives us a clue that something's changed, that something's different now. And we use SPC has statistical process control, has all kinds of rules to detect when there's a significant change. And it allows us then to monitor that process. And when a trigger occurs, is then, well, what's changed? What's different now? Is it materials or properties or environment or some other thing that's going on? When we're looking at field data, we don't have a set of rules that say this is different or not different. We may use confidence bounds, we may use standards or specifications or targets, or here's our forecast and it falls outside of the forecast. There's lots of techniques we can use to uncover changes as they are occurring. But even a simple plot, a simple CDF can trigger that something's not the same anymore. And so it's not always a true value. It might be just some randomness in our data set that the way the customers reported it, they may have been bundling things together. So our time to failure gets skewed and and we don't have a clear picture of what's going on. But other times there's really is a fundamental change in failure mechanism. And by paying attention and doing the appropriate level of failure analysis and understanding of the phenomena, we can take the appropriate steps and minimize the future failures if we can. But it's, again, just another example of a way of a plot in the use of statistics, and I'm not saying that all statistics is plotting, yet these simple tools allow us to ask better questions. And I think that's the value of statistics. It allows us to get insights into a set of data and data sets and lets them express themselves in a meaningful way that we can then ask better questions and get better answers. So, I mean, how have you used statistics? What has been the, here's the plot, that's obvious, we got to go investigate it, or this is insightful, this, we didn't know this before we did this set of data or this comparison or whatever. What works for you? I know in my own cases, when I get a data set and I do the initial plot, like that number 9 on that histogram, it almost always signals to me that I did a clerical error, that my handwriting's bad or my eyesight's bad or both. And if I have the opportunity, I go redo the measurements. Sometimes it indicates a measurement problem. The measurement system itself is, if it's not handled correctly, can really give you an outlier or a bad reading. Sometimes it's a clue that is there's something fundamentally going around different here. SPC being the classic for that. Yeah, manufacturing defects with Weibull plotting. Excellent. Yeah, there's ways to peer into the processes that we use and monitor and examine or performance of different systems that allow us to get insights to what's really going on. Now, it may not say, if I see a hockey stick on a Weibull plot, it's not obvious what changed just from that plot. But what it signals is that something's changed here. The slope of this line is changing. There's probably a reason for it. It might be benign. It might be just clerical error. Or we have a mixed data set that really shouldn't be mixed. Or there's something that's wearing out that shouldn't be wearing out. And we need to go investigate that. So it's the plots themselves and the data sets in and of themselves allow you to ask better questions and go pick through the data set to see what is really going on and dive into the phenomena that's generating that data. And it's to me, it's like the advances in mathematics have allowed physics, the field of physics, to make great advances. The questions being asked in the world of physics, say astrophysics, then prompt the mathematicians to improve their techniques and get more powerful methodologies to deal with the data sets that are available and the questions that are being asked that allow that back and forth between the phenomena and understanding of it and our ability to describe it and model it. And the same goes with statistics and many of the things that we deal with on a day in and day out basis, which is dealing with variability. Mastering the tools of statistics allows us to, one, describe the variability, but also understand it. And that goes back and forth. Statistics in and of itself is useless unless we actually use it to ask questions and do experiments and understand the world and either improve it or avoid failures or stuff like that. But if we just do statistics for the sake of doing statistics, well, there are jobs for that, I guess, someplace. But in our world, it's related to understanding the physical world and the phenomena that we are dealing with, whether it's making a product or manufacturing a product, and using that information to the advantage of our objectives in our organization and our customers. All right, so Michael's manufacturing defects, using stats, understanding of how customers may use the products. Yeah, That's often a great unknown, how people are going to use your products. There's plenty of stories out there about that, or where they're going to use them, or how often they're doing it. And then feeding that back into how you do your lab work. How do I qualify something such that it's meaningful? The better we model the use conditions and understand them, which involves lots of variability, the better we can, the more better is to use bad enough English, allows us to improve our design processes and techniques. So I was looking for obvious graphics for these various things and didn't really find anything, but hypothesis testing, somebody mentioned using hypothesis testing earlier. And, you've got a data set and a standard or a goal or objective you would like to achieve. And say you have a process that's creating something and average is 2 and you're getting 3.4. Well, is that good enough, right? Is that close enough to where you need to be? Or is it a signal that you need to reduce the average value and get it closer to your target of 2? So hypothesis testing can be used for a single data set against a standard or a goal or objective or a requirement, or it can be used to compare 2 different things, 2 different data sets. And it's great. There's ways to compare count data or binomial type systems. There's ways to compare and use variable data. We can compare variances using an F distribution. There's whole spreadsheets full or books full of ways you can do hypothesis testing. You can do paired comparisons where it's like a left foot and a right foot, and they're both seeing the same usage experience on the soles of a shoe. And you can randomize that. So some of your sole finishes is on the left foot versus the right foot and so on like that. And different people, different walks of life, no pun intended, that allow them to compare the performance of the durability of, say, soles on a shoe. But because they're paired with the same weight and stride and gait and all those other things, then it gives you a different kind of insight to what's going on. Because if I gave the same sole material to 5 people over in the Northeast where it's pretty cold right now, or and snow on the ground, versus 5 people in San Diego, and they're at the beach, they've got completely different textures and environments affecting the performance of the wear that we're trying to measure. So by splitting them up and using hypothesis tests in a creative way, and there's plenty of people that have created, I don't know how many different types of hypothesis tests that are out there. I think sometimes it's harder to figure out which is the appropriate test than it is to actually run the test. Minitab and other packages have so many different ways to do it. Most of the math for these things is pretty straightforward and a little bit of effort, not much. You could put it up on Excel in short order, but it allows us to compare and get some insights. Is this better than what it was before, or is it different enough that it's worth doing? Is it saving us enough money? Is it improving the yield? Is it real, or is it just random? And so it gives us insights that allow us to take, say, 2 histograms that are stacked next to each other and say, yeah, that's a real difference, versus that's likely a real difference. I should rephrase that, versus that's just random chance. And so sample size starts coming into this. That's subject for a whole nother podcast or series of articles. But it's to me, it's the gateway analytical tool into statistics. It's one that we all should be familiar with and master. Another one is ANOVA. Now this one in its use tapers off dramatically from histograms. It's a little more complex. It was created before calculators were predominant. And so we get sum of squares, we get all these arcane terminology and the ANOVA graphics are full of SS something, sum of squares of something. And sometimes we add them, sometimes we, stack them up and get ratios and do all these other cool stuff with this thing. And the math was all created well before computers. But what it did is it solved the problem when I have three things or more. I want to compare 4 kinds of fertilizer. And I want to know which fertilizer is better than the other ones at growing grain, for example. Well, if I do a set of two-way comparisons, I start really losing the ability for that technique loses its ability to detect true differences. So if I have enough difference, or say 4 sets of data, the likelihood of seeing a false positive goes up dramatically. Whereas an ANOVA sidesteps that and allows us to make these comparisons for 3 or more data sets. Now, it's an easy one to detect. If you got 3 vendors and you're running them through a set of paces that you want to make some measurements on, and you want to detect which of the 3 is different, and hopefully in a better or worse way, ANOVA is the tool to use. It avoids some of the downfall of making a set of two-way comparisons. Now, it also is much like a hypothesis test that allows us to separate what is random and what is likely a real difference. So like hypothesis tests, it has lots of great features and benefits, yet it's a bit more difficult to master. And like hypothesis tests, there's a whole raft of different ANOVAs. But once you get the hang of them, and the hard part I find is explaining it to other people. And we say, and then we do the sum of squares of this, and then we have this ratio, and then we compare that to an F distribution. And by that point, you've lost half the room, probably lost half of you, right? But the idea is that it is the appropriate tool. And if you understand it well, you can explain it. And that's the hard part for me, is being able to explain this slightly more advanced tool in the world of statistics so that other people understand that the results are meaningful or not meaningful. And so then you get into design of experiments. Now, we can do screening, we can do comparisons. We use ANOVA as one of the techniques that's built into design of experiments. We often use computer systems now to do the math for us, even though it is really pretty straightforward. But you have to pay way more attention to how you set up and organize your experiments. And the worst thing you can do to a statistician is go run a bunch of random experiments, and you're trying to create some new product, and you're working with different material sets, and you tried this, you tried that, you made all these measurements, and you give them a stack of data saying, I made all these measurements, can you tell me what it means? Well, if you would have only thought about it a little bit earlier, you could have done a design of experiments that would clearly give you results that are meaningful. But just doing random samples not random samples, but random sets of experiments and random different combinations of inputs on it, the chance that you actually create a meaningful set in aggregate that gives you meaningful results is very, very low. But stepping back and thinking through, I got 3 different materials, I got 2 different processes. How do I optimize this so I get the results that we're looking for? Well, design of experiments is your technique. And oftentimes, whenever I've gotten involved with DOE, it's been after the random walk kind of approaches are just not working. And then somebody says, we need to do something better. And here again, there's a dramatic drop off in what I've seen anyway, of people using this tool versus other statistical tools, because it does have a bit of a learning curve. It is more powerful, yet it also is harder to explain. And it's more better. Every time I say that, I think of Mrs. Fink, my 6th grade teacher in English classes. But the idea is that it's the right tool for a good number of things that we do in the design world or in process world to improve our understanding and optimizing of systems. And it's another one of those things that, yeah, it takes a bit of work to do it. Somebody, I think it was Michael, mentioned doing regression analysis. Now, there's all kinds of levels of regression analysis, and you can get into multi-dimensional space basically and create fits and modeling of all kinds of exotic things. Or you could do a simple XY plot and draw a line through it. Like DOE, you can do simple stuff, but the tool is so powerful, and it allows, well, let me just put it this way. It's the right tool when you need it, but it does take some more work to get to it. And it's in a deeper end of statistics for most people. And it does take upfront work and thinking it through to be successful with it. Now, I'm only scratching the surface of the range of statistical tools that are out there. Now, by far the simplest and easiest is just do a plot, all right? Get started with that, get some data and plot it. And my master's program in statistics, that was over and over and over again in all kinds of classes. Do a simple plot. It's just see your data, visualize your data. It helps us grasp what's going on so much better than just a table of numbers. Now, everything we do after that, whether it's hypothesis testing or DOE or regression analysis of one sort or another, it allows us to refine our ability to understand the phenomena of the variability in our world around us. And that's what statistics does. That understanding then leads us into the ability to ask better questions, to probe that data. Why is that one dot over at number 9 so far away from everybody else? And what's going on there? Now, that's an important question. A lot of times, statistics itself cannot answer that, but it does let us ask better questions. Sometimes the data set and the models we use allow us to peer into the phenomena that we're dealing with and make predictions and projections of what's going on and detect changes before they get out of control. To all of these different phenomena is why we use statistics. So reliability engineering, to me, and this is probably a function of how I got started in reliability work, is really statistics. It's a big part of our bodies of knowledge for how we use it. And a concerning piece to me is the ongoing resistance to even using basic statistics or understanding simple things like what a mean value is and how void of really useful information it contains. Being careful about how we gather and present data is statistics. And in reliability engineering, we're dealing with variability. And so we have to use statistics and use it well in order to do our jobs well. And so for those that are, knee deep in stats and use it all the time, this is preaching to the choir, essentially. For those that are shied away from it, well, it's worth exploring and polishing up your skills in those areas. Plenty of different sources out there for figuring this out and using it and learning the techniques. But by far the easiest, best way to do it is just try it. If you have the opportunity to do a comparison, if nothing else, do a hypothesis test or do a histogram with both data sets on it, and then do a hypothesis test to do the next level of statistical insight into those two data sets. Just try it. If you have questions or you need help sorting anything out, there's plenty of resources out there, myself included, where you can ask and learn these techniques so that you can get better at mastering the world of tools that are available in statistics. And that will improve your ability to create reliable systems. And I have no doubt in that. course, there's variability, but hopefully it's an improving one as you master these tools. So that I actually finished on time. I almost never do that. So I'll stay on the line if there's any questions or comments, but that ends the formal presentation of this. My intent is to use this recording on a page about statistics on Ascendo that helps people find these tools and techniques and tutorials on them, plus more information about many of the other tools and techniques that are available. So that's my intent with this recording, and I appreciate you joining me today to take a look at it and ask a few questions and participate. But I'll end the recording here and I'll stay online to see if there's any other questions.